So knowing what we know about equilibrium constants and what they really tell us about the ratio of products to reactants when the system is at equilibrium, let's look at an example and see if we can use that to understand if a system is at equilibrium, and if not, which direction it will proceed in a reaction, whether forward or reverse, to achieve equilibrium. So example I have written up here is hydrogen gas plus iodine to make hydroiodic acid. And we know that it has a K of 57, and that's at 500. So let's pretend we have this round bottom reaction vessel and that we have all three of these species, H2I2 and HI, and we inject them with a syringe all at the same time at these three concentrations. So the first question we can ask is, well, how is this thing going to proceed? Which direction is it going to go? Are H2 and I2 going to go and make HI to reach equilibrium, or is HI going to decompose back into these to reach equilibrium? So let's look first at our intuition, knowing what the size of K is, given the reaction as it's written. Well, K is 57. Remember, if K is 1, that means we have equal parts products and reactants. If K is greater than 1, that means we have more products in the system at equilibrium than our reactants. So we have all of these known concentrations. Let's start by writing up the equilibrium constant expression for this, and then plugging these things into that equation. So the equilibrium constant expression looks like this, just products over reactants, each of which is raised to the power of its coefficient. Here 2 for HI, don't forget. What we don't know about the system is whether these three concentrations, which we could easily substitute in for the variables here, we don't know if those are all going to be at equilibrium. And so instead of writing the next expression with a K, we're going to use this thing called Q, or the reaction quotient. It's the same thing essentially, but Q is used when we're using concentrations that we don't know if they are at equilibrium, because right, that is the question, is the system at equilibrium? So what we'll do is just plug in values for HI. So HI first is 0.4, and that's squared. H2 is 0.1, and I2 is 0.2. So we can solve this to give us a reaction quotient, and then that reaction quotient can be compared directly to K to see where this system lies and whether it's going to proceed to reach K by increasing or decreasing the reactants. So the value for Q, if you compute this, is 8, and remember K is 57. In that case, the reaction quotient, which is, remember, just using the actual concentrations of stuff in this vessel, is less than K. The value is less than K. What does that mean for the direction this reaction will run? Well, for Q to make K, to equal K, right? When Q equals K, that's when the system is at equilibrium. Q doesn't equal K, so which direction will it proceed to reach it? Well, it has to increase, right? Sort of intuitively. If Q is increasing, then what's happening to the species? Well, that means that HI has to increase while H2 and I2 are decreasing, right? That's increasing. These are decreasing. That's going to result in a net increase in Q, and that's going to proceed by having the reaction go from left to right. So that would be the direction this reaction would run if we charged this vessel with all three of these species at these concentrations. Where would it stop? Well, it would keep going until the quotient Q is exactly equal to 57, K for the reaction.